I've actually been using Analytica, and this will date myself now, since 1996. I was even using it before it really became available as a commercially available product. I think we had a bootleg copy of Demos, and not long after we started using that copy, the commercial available version came out. So it kind of tells you how long I've been using Analytica, and even should give you some idea about how old I am. But anyway, so primarily I do use Analytica on a daily basis in the work that I do as a analyst, a strategic analyst within Novelis. Right now, I am housed within the global automotive group, and we are focused on helping people to adopt the use of aluminum in the design of their automobiles. So many of you may also be aware of the Ford F-150. The Ford F-150 is about a 95% aluminum vehicle, and we supply a good proportion of that aluminum to Ford as well as other auto manufacturers. But I also spend about 50% of my time outside of global automotive, meaning that there are other groups within Novelis that have expressed need for a decision analytic viewpoint to various project analyses or strategic planning efforts. And so in many cases, I participate with those planning projects to do the modeling that's associated with that. So instead of using typical spreadsheet type basis for that modeling, we use Analytica, and it heavily relies on the characterization of uncertainty, and also, as you'll see throughout the upcoming demonstration, the use of the intelligent arrays and multidimensional expressions of or representations of tables within Analytica, which is one of its most powerful features, by the way. The other thing that I will point out, though, and let me sort of state this as a disclaimer up front, I will be taking the time to go through a variation of a model that we used recently. By variation, what I mean is that I've simplified it to some degree. I have changed all of the input numbers or the values that go into the inputs of the model so that they are completely anonymized. They don't represent anything sort of similar to what we would actually use in a real model. And secondly, I'm going to be introducing a methodology that we have begun to consider using. We have not yet decided this will be our primary way of estimating the burden of CO2 in our efforts or our planning efforts. However, it is something that we are actively considering, but it is still experimental, and it is not, let's say, a confirmed and decided upon methodology. That being said, I mean, I do emphasize we've used it a couple of times at least to help guide our thinking. Moving on from there, I thought also I would ask maybe for those of you who are participating, how many of you do have some background with Analytica? Maybe if you could just indicate real quickly in the chat room feature, what level of experience you have with Analytica. And then maybe after you've answered that, or in addition to that, indicate how you may have become aware of Analytica and what maybe caused you to be interested in participating in today's webinar. So I'll let you sort of pop those into the chat to the group. But I'll continue to move on from there while you're thinking about that. So let me go back a little bit and introduce Novelis. So Novelis is actually the world's largest supplier of aluminum flat rolled product. So if you're familiar with aluminum foil that you keep in the kitchen, we make very large rolls of what are essentially foil, although I think foil has a technical definition of having a certain thickness, less than, some fractions of a millimeter. Typically, the foil that we make is a meter wide or more in length that is the rolls, and the thicknesses of the sheet are only order of 0.5 millimeter to maybe 2 or 3 millimeters. As you may suspect, what this flat roll product is used for, based on some of the names of our customers that you see on this list, is this foil is used in the manufacture of their products. So we supply a large amount of the flat roll product, or FRP, as I'll say from here on out, for beverage cans. So if you think about Coca-Cola, Ball cans, Pepsi cans, or Crown rather, just about all of those aluminum beverage cans come from, or probably do come from, our source product. Automotive, of course, the sheet that goes onto the skins of automobiles. Many automobiles use aluminum for this. Primarily, one of the first pieces of a vehicle that usually converts over to the use of aluminum are the skins. Usually it's the doors or the hood or the lift gate. But in the case of, say, the Ford F-150, we also contribute a significant proportion of the aluminum that goes into what is called the body in white, meaning the structure, the frame structure of the vehicle. So we take this flat rolled product, and Ford or other manufacturers stamp that flat rolled product into shapes and forms that then are used in the structure of these vehicles. Of course, you see we have some aerospace. So recently we completed the purchase of Alaris to broaden our overall portfolio to include now aerospace products. So usually when you're flying in one of the large commercial aircraft, those aircraft skins are made by, or in many cases supplied by, our products as well. And then finally, we also have a specialties division where we provide different kinds of actual foils to electronics or other aluminum, FRP-based solutions that are used in usually small run batches or things like that. Usually they're not our largest, let's say, ongoing perennial consumer. They tend to come in waves or in short contracts. The interesting thing about all of these products, though, as you may suspect, is that they are all composed of different types of alloys of aluminum. So the beverage can uses one alloy. The automotive industry uses probably 3 different types of alloys. Aerospace is a completely different type of alloy, as well as there's another range of alloys that are used in the specialties vertical. So there are a number of different products that we have, and each of these products require different amounts of energy to create. They each have their own sort of contribution margin back to the company. And we also negotiate different prices for our products. So there's a whole mix of financial as well as underlying technical considerations that are made when we develop various strategies or plans to deliver new products or to expand, or to engage in capital expansion to supply a new set of products. We need to make sure that those products are balanced in such a way that they satisfy not only our customers' requirements, but they also can deliver a rate of return that is exciting or interesting to our primary shareholders. The problem, though, that I should go back to and mention is that, as I mentioned, that each of these products have a different range of energy contribution to them. The effect of that is that these different products are then the source of different levels of CO2 and other greenhouse gases to the environment in their manufacture and delivery to ultimately our customers. This is particularly the case if a company were to rely solely on prime aluminum, and that is aluminum that comes directly from the conversion of alumina into aluminum. So I think most everyone is familiar with the silvery metal that they've seen as aluminum. But prior to being aluminum, alumina is in its elemental form as alumina, or it's I should say it's post-bauxite conversion into a form that is stable, and that is alumina. It's sort of a dark red powdery substance. Converting that alumina into aluminum, and that is a form that is usable in commercial and industrial applications, requires a huge amount of electricity or energy. We use electrolysis. This is a historically enabled process that the industry has used for probably close to a century now. And it just simply requires large amounts of electricity to drive this electrolysis process. So kind of jokingly, I often tell people that aluminum is sort of solidified electricity because of all of the electricity that goes into converting or transforming alumina into aluminum. Those conversion efforts, of course, use a lot of energy or release a lot of CO2 if they are not based in hydroelectricity. So if hydroelectricity is not, or supplied electricity is not the primary source, then the alternatives would be, of course, nuclear. So if you happen to be near a nuclear producing station, you can get that energy. That's also low in carbon, but unfortunately, the other alternatives are much higher in carbon, in their carbon footprint. Namely, that would be coal and natural gas sources of power. So what we are trying to do and hoping to do, of course, is to diminish our reliance on the amount of prime that we use in our products. Now, we are not necessarily a manufacturer of the prime, but we do source prime or bring prime, purchase prime into the production of our products. And as a result of that, we are responsible in some way of bringing that CO2, that the footprint, into the market as well. So one way we can do this is by reducing our reliance on prime and, say, using more recycled content. And depending on which business group that we're looking at, we have a very large amount of recycled content. I think it ranges, and I'll be honest, I'm just sort of guessing right now, but I think it's somewhere between 60 and 90%. Again, depending on the business unit, of our aluminum comes from recycled content, and we obviously want to get that much higher and consistent across the board. So we have a plan to do that, and we've committed ourselves to achieving a 30% reduction in CO2 footprint by 2026, as well as the much longer range goal of achieving carbon neutrality by 2050. So I think that sort of implies or indicates that we can't do this overnight, right? So it takes time to make this transition. We have to have all of the sourcing lined up. We have to have a way to transition from prime usage, and we have to have a way to improve the overall contribution of the aluminum recycled content. So let me just please ask you, if you do use aluminum beverage cans, if you don't mind, please set those aside when you're finished using them and getting them to your recycle location, because the net effect of using this recycled content is that it reduces the overall carbon footprint by about 95%. It's a significant avoidance of CO2 contribution by relying on recycled aluminum. So that's our plan. And I would also say that we've put our money where our mouth is, or our heart is, if you will, in order to give us the incentive to make sure that there is a true economic incentive that is right in our own backyard, that is driving us to make sure that we adopt these programs or projects that actually do reduce CO2 according to the schedule that we've laid out. So we take this very seriously. And so we haven't just made, market-facing comments, or we have actually put our money to back our mouths up. So with that being said, we now face, of course, a bit of a trade-off, right? Because if we are going to pursue new projects associated with capital expansion, we have to make sure that we are pursuing these very audacious goals of CO2 reduction, while at the same time trying to achieve rates of return that still keep our shareholders happy. This is a very complex set of trade-offs that are often required, and it's not necessarily easy. So what this is ultimately getting to, I suppose, is we have been thinking internally about how do we get to a point where we can make equivalent trade-offs between a dollar produced that goes to our return on investment versus the CO2 that we also want to reduce, right? So a kilogram of reduced CO2, we need to balance that against a dollar of return on capital invested. And make sure that we're sort of pursuing both of those objectives in a way that as best as we can makes as many people as happy as possible, including ourselves. I mean, we're going to be breathing the air that and I guess experiencing the effects of global warming as well as everybody else. So we have a stake in this that goes even beyond just the money that we've put up into these various bonds that we'll issue. So having said that, maybe let me pause here for a moment and ask, are there any questions before I kind of move into the Analytica model itself that I'll show you? Well, if not, I'll start here. So again, if you're not very familiar with Analytica, I'll kind of cover some high-level concepts behind the tool. And maybe this will sort of help you get some deeper insights into your use or potential use of Analytica. One of the reasons that I really, really like Analytica is the fact that it creates an immediately visually auditable trail of the thinking and the logic that goes into a model. That trail is sort of represented with something that is similar to an influence diagram. However, there are a few variations on this. The first is that influence diagrams in Analytica can be subdivided hierarchically into modules. So if you think about comparing this analogically to a spreadsheet, worksheets within a workbook are the analog of modules within an Analytica file or an Analytica model. So they represent submodels, if you will. I can double click on one of these modules, and that takes me to another level, another layer. And within that layer, I can also build out these various nodes that contain either input values, which my sort of standard practice is to represent inputs with green variable nodes, and let intermediate calculations fall within the blue nodes that you notice, the sort of the rounded shape, the rounded corner parallelograms. And so by following the arrows throughout the model, I can very quickly get an understanding of how the model is constructed. And if I open up one of the, let's say, the windows, sometimes takes a little bit, but I can open up the object window associated with a given variable and understand its underlying definition in terms of an algebraically constructed formula as opposed to a row and cell referencing kind of formula structure, which I think makes it almost immensely better than spreadsheets at this point, because now instead of trying to understand the variable relationships within a model on the basis of where they point to, let's say geographically within an Excel model, Analytica is more like an object-oriented environment where I actually operate on other objects by referring to their name. And so Analytica actually operates on the entire object unless I give it some sort of conditional, logic to countermand or override the sort of the default language structure underneath, which you do very frequently, but just as the default, that's the way Analytica works. Every element or every variable name that you see here is being operated on in its totality. Of course, then the object window gives us the ability to specify what the title is of this variable, as well as its unique identifier, which is the actual reference to the object that we use in the explanation or the definition of variables. There's a description field, which admittedly this should be filled out, but I have failed to do my job appropriately here, I guess. But I should provide some little explanation of what the variable is actually doing within the model. Of course, capture units. There's a list of variables that tell me what goes into this particular object, as well as a list that tells me every next downstage reliance on this object. And you can also see here, these are not necessarily part of the default set, but I've added user-defined fields here for myself, where I've added a reference field and a notes field. So in addition to the description that I may provide when I'm actually doing my job better, I can provide, where I may have developed or what resource or citation I may be referring to when I've developed this particular variable, as well as any other additional notes that I wouldn't necessarily put, in the reference field or a description field. Maybe, to-do notes or things that probably should be worked on in a later fashion or at a later time. So, of course, as you can see, I built this sort of model to represent the entire economic consideration for a given project. This is, as you'll eventually see, it's one project, it's a capital expansion project, where we've defined approximately 7 different strategies to compare to each other to make comparisons and contrasts, ultimately to help us make the final decision. I'm not going to go into every one of these modules, primarily because even though I have changed numbers, there are some object titles that are somewhat proprietary, as well as there's some underlying logic in any of these, regardless of the numbers that are used. The logic itself is still somewhat proprietary. But I think you can see sort of the structure, starting with the capacity that we have. There's a sort of a back and forth relationship between our capacity that we have online today versus capacity that we want to build. And there is an interaction with the overall unconstrained market demand that ultimately gets us to a constrained market demand that is filtered to our particular product lines. Of course, once we know what that demand is it's constrained by capacity, we then can calculate how much supply we generate back to the market, what the CapEx would be required to satisfy that supply requirement. And then, of course, any of the OpEx or other contribution values that derive out of that. So one thing I will point out would be that in the value module, all of this ultimately gets me to this sheet where I have a P&L. This P&L, of course, works its way down to finally incremental cash flow against our baseline strategy. And ultimately from that, as a typical calculation for every strategy that we would be considering, I can calculate a strategy net present value. Now, if I click this, let me turn this off and put this in cumulative probability form. So I think from this screen, you can see now that when I look at these various investment strategies, which I've, again, changed the names to sort of protect the guilty. So we've got about 7 different strategies. So we want to maybe keep one particular line. We're thinking about, in this hypothetical strategic consideration, we're going to keep one particular line of business. We want to expand that into, let's say, bicycles, as well as AFH, which could be aluminum foil hats, maybe. And then, we may also consider getting out of that particular one particular line of business. But as you can see, what this is displaying are the cumulative probability profiles, or the risk profiles associated with the value creation of each of these various strategies. So immediately I can look at these and say, well, there's a clustering among these strategies, and I can go ahead and particularly get rid of probably these first four that you see on the left-hand side from this farthest right-hand side, because they are no better by comparison than these three over here. But these three are rather close together, so they may be worth paying some more attention to. So if I were to make a decision primarily on the basis of the net present value that is generated from these projects, this would primarily be the end goal of my analysis. I want to get a view of the total value range, the overall probability associated with maybe the key interior points, so an 80th percentile range of value. I want to look for where the strategies may cross over so that I can see if they're maybe conditional situations in which some strategies edge out another strategy, which would then potentially lead me into some deeper trade-off analysis or sensitivity analysis to understand what's causing this separation in this upper tail. All of that's standard, strategic analysis work that you would do with probabilistic reasoning and simulation, Monte Carlo simulation running in the background to support it. But as I mentioned, we still need to make a trade-off between this viewpoint, or this set of objectives to guide our decision making, with the amount of CO2 that gets created. So what we have is another module where we look at the supply that we would generate conditionally for each one of our strategies, and we look at how that CO2 is generated on the basis of various products that are associated with the strategies, as well as how much of that product gets generated. Now, we also have behind all this, so of course, you might be wondering, how do we get those CO2 values? Well, we do have sort of a certain sourcing mix. So if we know where this aluminum, prime material, or the recycled material is coming from, no, excuse me, I thought I had that turned off. Then we can understand what fraction of that material is prime, and how much of it comes from different regions. So I'll click this regional sourcing mix button, and you can see what we have here is the source mix, the prime source mix for each of these energy sources associated with each of the regions. So our source aluminum that goes into, from in ingot form, that comes into our manufacturing facilities, that gets converted into flat rolled product, would come from any one of these regions according to any one of these energy sources. They're generated, those ingots are generated using these energy sources. And we have this set up so that we know what that sort of time frame looks like. So in 2020, the sourcing mix, had a certain level. It does change a little bit over time, and I know now that this is a little dated because these numbers have actually improved over the last year and a half from when they were originally generated. So people are taking this much more seriously just recently, and they are also making plans for how they shift the source, the energy source of the production of ingots. So with that, and also knowing how much each one of those sources contributes, let me get this table. We have a standard set of burdens, if you will, burden factors associated with each one of those energy sources. Coal is the worst. Right now, we sort of estimate that at around 21.1 tons of CO2 per ton of aluminum that gets generated as finished goods. And then secondly, followed by coal and gas. Gas comes down the line a little bit more. You can see that hydro is better. And we ultimately get down to nuclear. We would love to see more prime being generated with nuclear as a power source behind it. Of course, the best is altogether using recycled aluminum because it doesn't rely on any of these sources. So that's what we describe as our scope 3 metal coefficient, or scope 3 metal contribution to the production of aluminum finished goods. There's also another level, a scope 1 and 2. This is more proprietary. I can't actually show this number per se, but this is our own rating, internal rating of how the internal support energy sources contribute to the CO2 footprint as well. So this would be, running the plant itself, transporting material, things like that. In the end, of course, what we have is a total CO2 burden across, the various choices of strategies that we created. So, this third strategy actually has a net contribution against the baseline of CO2 reduction, whereas these others still contribute quite a bit over about I think it's about a 12-year horizon in the model. So, we'd be looking at, for a given strategy, the worst case being somewhere around, 12.5 million tons of CO2 per ton or associated with the total aluminum finished goods product that comes out of this particular strategy. So if we compare both of these curves, of course, this is a little difficult to make a clear distinction. Well, okay, I see I can make a lot of money over here using these strategies. As you can see, this strategy that produces the least amount of, or this strategy which produces the least amount of net present value, also has the greatest probability of failure. It actually produces a very small amount of CO2. So, and of course, this strategy has a net reduction in CO2 overall compared to baseline, but it's associated with this particular strategy, this fourth one over. So that may be a little difficult to actually make a trade-off in your, just by visually inspecting that. So then the next thing we might want to think about would be, if I look at the overall CO2 burden compared to that net present value, I can look at that as a scatter plot. So Analytica gives you this ability to produce scatter plots. But again, as we look at this, you can see that, yeah, maybe the yellow strategy, which produces the highest net present value, it's also producing the highest, it appears to produce the highest CO2 contribution. That we probably not want to automatically pursue that strategy because, again, it's the one that gives us the highest CO2. So we might think about coming down the line. So if we can move vertically downward and find strategies that have a lower amount of CO2 contribution versus the overall net present value generated, you can see that it's probably going to be a trade-off or some sort of comparison between these strategies represented by these strategy names here at the bottom right. However, again, it's not altogether clear exactly which one is best, particularly among these two. There may be other reasons why we might still pursue these strategies, even though this grouping or scatter of CO2 outcomes are the lowest. So another way to think about this would be to convert the CO2 generated from a kilogram production level to an actual dollar level, and then do a dollar-to-dollar comparison. So that's sort of where the meat of all of this is heading. How do we do that, or how can we do that? So if I go back to my CO2, what I've done is created a way of looking at the way the market thinks about valuing CO2. So primarily, I think credit markets exist for this. And my sort of operating idea here, and I'm not necessarily saying it's exactly right, and that it couldn't be modified or even criticized, is that those credit markets represent a kind of a clearinghouse value for what people think it's worth to actually buy a credit versus actually installing or taking into consideration the actual managerial actions to reduce CO2. So I went back in time and I looked at what those carbon prices might be over a very long history. And as you can see, going all the way back to 2008, this is what the European credit market looks like over time. Those credits became devalued in this time frame, but as of 2018, those credits began to accelerate again in value. So maybe this has some way of informing me how I should think about the value of a CO2 ton produced. So my thought was, well, what if I look at that volatility, not necessarily look at the prices per se, but the volatility, take those weekly returns, turn them into daily returns, and then, you know, I'll open up the formula for this. I'll calculate the weekly returns, which now this employs the use of Analytica's dynamic function. So as you can see in this formula here, I'm going to use the market index dates as my time index, my local time index for this particular node. And I'm basically going to look at the weekly returns from one week to the next, and then look at the relative volatility of that over time. So if I run that, you can see now I get a profile that, upon visual inspection, I admit, it's pretty flat. It doesn't look like the volatility itself is necessarily drifting, but as you can see, there are periods of high volatility. So if I were to take that, convert those to daily returns, and then calculate an actual cumulative or an empirical CDF or cumulative probability distribution of that, Analytica has a function that allows you to do that. It's basically just CDF. So if you specify the actual values that you have that are spread over some index, and then indicate the index over which they are generated, Analytica will then specify what that probability, that empirical CDF looks like, along with the associated percentiles with each bin in the output. So with that, I then recalculate the future of the forward-looking prices based on this probability characterization of that credit market. Again, these are in euros. So when I run this, and I'll put this into probability bands over time, that gives me the volatilities over a period of about 10 years. And then when I run those volatilities against the starting point price, you can see I now sort of get a full evolution of the price starting from some price basis that we'll call today, today, and then see how that evolves over time. But again, this is not necessarily in my time index that I'm using for the other master model. This is in the number of days simulated forward, because I'm actually going to try to do something else. Instead of matching this to the current forecasted evolution, I want to bring or sort of take this away from the actual credit market and convert it more into a representation that represents, let's just say, the overall market valuation for CO2 reduction. And I do that by converting this time-based distribution that I just showed you into something that I'll call a dwell price. And what that dwell price is really the marginal distribution of that curve over time. So that when I take that, get that marginal distribution, on average, it's worth about 50 euros per ton. Or if I look at it in terms of a cumulative probability distribution, I get a range that goes from around, let's say, $69 or $70 per ton, all the way down to, it looks like maybe about $32 per ton would be the 10th percentile. So 80th percentile estimate that the value of carbon to the market, that is the cost of the value of reducing that CO2, is somewhere between $30 or $32 and $70 per ton, with a central tendency somewhere in this $50 range or €50 range. That's in euros. We don't have a market for CO2 in the United States in euros or even in dollars. So I actually followed the same process with the exchange rate and came up with more or less a, let's call it again, a dwell price for the exchange rate of dollars to euros. And my units are incorrect. That's something I should correct myself. But as you can see, what it gets me is somewhere around 14% exchange rate on top of a dollar. So when I now multiply these two distributions by each other, I get an overall dollar figure of $60 or around $61 per ton, and then a full distribution that could go out as high as $200 a ton. But the 80th percentile range is somewhere between, let's say, $90 a ton and a little bit higher, $36 a ton. Now, again, this represents a price. It's a mythical price, a hypothetical price that we would apply against that CO2 tonnage that we produce as product. And I would multiply that burden, that CO2 burden, times the credit price that I've just generated. And that number would then go back out to my strategy net present value calculations. Make sure something. Yep. So now I have a set of dollar figures that I can subtract from my net present value to readjust the value of the normal economic rate of return calculations to account for the value of the CO2 that's generated. Now, let me point out, I will not discount this against time because this is not an actual expense that will occur. It is a way of, let's say, equilibrating a dollar of return against a ton of CO2 produced. So by doing that, taking this calculation back over here to my net present value calculation, I will now convert this to a display into mean values. So again, if you're not very familiar with Analytica, Analytica provides you to switch back and forth between different summary types of the underlying simulated values in a given result. So here, of course, I'm looking at cumulative probability. Let me make a quick shout out for this. Lumina has just recently added the exceedance probability. So it's really 1 minus this curve. And instead of seeing those curves as typical cumulative probability and thinking of them as the probability that a certain value or less will be achieved, in this particular case, if you're not familiar with exceedance probabilities, I can look at this in terms of what is the probability that a certain value or greater will be achieved. And I read the y-axis exactly the same almost, except that I'm thinking instead of less than, I'm thinking greater than. Let me go back now. What I was going to do is compare these on their expected or their mean values. And I'll need to sort of switch the credit cost into the chart. So now if I look at only the expected values of the net present values of each strategy, those are represented with these sort of red bars. If I burden each of those strategies with the value of the CO2 the way I just described, you can see now that I've got some pretty clear distinctions that can be made between my two best strategies. So before, if I looked at these only in terms of these, the returns that each generate, I would have to sort of think about what is causing the difference between this strategy and this strategy, because these are really my two best strategies. They have almost exactly the same economic value. But then when I add in that social value of carbon, this strategy has been significantly reduced in its overall value. And this strategy is now, it moves sort of into second place compared to this strategy here, which has been improved because the net CO2 that was generated by this strategy is actually less than our base case strategy. So now I've more or less prioritized the value of my strategies based on this social cost of CO2 burden that I've added or applied against each of those strategies. So I think that kind of takes me more or less to the end of the description of this model, how we thought about putting it together from a typical economic evaluation perspective, and then loading it in, and then loading against those evaluations the value or social value of carbon to get us into a reprioritization of the choices that we would otherwise make. So I guess maybe I'd stop there and ask, are there any questions or clarifications maybe that I can address in our remaining time? I'll have to scoot a little bit closer to my screen here because I'm also nearly blind. Okay, let's see. If you grow your production, in some cases, you displace an alternative. That is, a customer using a different material or purchasing from a different aluminum company with a different CO2 burden. Do you think your metric should include the delta between Novelis' CO2 burden and the alternative? This comes from Lonnie. So I have to admit, that's kind of a difficult question to answer, but it is probably the case that we should consider the overall net effect to the market, right? So if we displace something and we move that to another consumer, then yes, the same amount of CO2 would probably still be produced, and maybe even more if they are not as aggressive in their use of recycled content as we are. Does that kind of try to address your question? I think it would be responsible. I don't know if, how we would actually get to their particular figures in a meaningful way, though. That would be our competitors. Yes, it would be tough, right? I'll take any other questions or comments? Maybe even not so much about this particular model per se and what it was trying to accomplish, but about Analytica in general. Well, I don't see anybody offering any questions at this point. So Mitsu, I'll turn it back over to you. Let me just end by saying I hope this was informative to everybody and at least helped you to see two particular, I think, viewpoints. Number one, how a particular company does use Analytica to make complex trade-offs. But secondly, maybe how to think about in your own industry how your CO2 footprint is calculated, and then to understand what sort of steps you might take to also make equivalent trade-offs between one strategy versus another that also has different differing levels of CO2 associated with them. Let's see. I'm going to turn the host back over to you, Mitsu.
Thank you so much, Rob. Sorry, I think I got stuck on mute. It looks like we just had another question come in from Adam. He said, can you change the number of simulations in Analytica?
So if by that you mean the number of trial values, yes, you can. So if you can still see my screen, the way to address that is to go to the result menu item and go to uncertainty options. And here you'll notice that the sample size is selected as 1,000. That is my default uncertainty level for sample size for these models. I'll make a point about this. I actually had this conversation with somebody yesterday, and not even really discussing Analytica. We were just talking about Monte Carlo in general. 1,000 samples generally for most business case analyses in Analytica is quite sufficient. Primarily because Analytica employs a form of Monte Carlo simulation called median Latin hypercube sampling, which you see as the default sampling method chosen here. It's a lot less noisy than, I would say, typical simple Monte Carlo. And what I mean by noisy is that if you take a Monte Carlo simulation, run it, say, at 1,000 samples or trials, calculate the mean value of your objective function, and then rerun that same simulation using a different seed but the same number of trials, the mean value or the expected value will not necessarily conform, in many cases, very closely, depending on how nonlinear or what sort of the level of the nonlinear effects you may have in your model. In fact, it may even be strictly linear, and you'll still see this sort of wobble around the mean value. So if you repeat that process over and over and over again, you'll notice on different seeds you get a different mean value. The median Latin hypercube sampling actually preserves the overall shape of the underlying distributions much more coherently, I'd say, or consistently. And as a result of that, the mean values between runs in Analytica are pretty stable. There's hardly any variation at all. So anyway, to answer your question, this is how you change the number of trials. And typically, I would say that unless you're doing something that does require a different sampling method, using the median Latin hypercube sampling is really one of the better options to start with. Any other questions? I think we've got about 3 minutes left.
Great.
Yeah, sure, Adam.
A couple of quick announcements just while we wait if there are any other questions. I just wanted to note that if you are an Analytica user, our 6.0 release has just gone out.
Yep.
A ton of great updates, and Lonnie, not to put you on the spot, but potentially if you wanted to speak about anything there.
Hi.
Hey,
So
Lonnie.
hi. As far as a comment on the 6.0 release, I guess we're just excited to have crossed that, and I'm always working through it. So it's always exciting to get to a milestone like that. So hope people enjoy it. And,
yeah, we've definitely got some positive feedback through our channels about the release, Lonnie. And just for those of you who aren't aware, Lonnie is our Chief Technology Officer here at Lumina Decision Systems. So he's the brains behind the software, and he does a lot of work on maintaining and updating it on a regular basis. So yeah. Great.
Yeah, I got one yesterday from somebody. It's really the kind that make you feel really good about your job. I'll tell you. So it was like, he was like, 6.0 is great, and he went on and on and on. I was like,
yeah.
Oh, what? That's nice to get that.
It's
kind of
small,
enthusiasm.
I think it's a small feature that in the scope of things is probably not the most important thing you've added, but I really love the fact that we can now put broken or bended arrows in the diagrams. I have been making a lot of use of that in all of my diagrams lately, so thank you.
Good.
Fantastic.
Good. So.
Okay, well, thank you again so much, everyone, for joining us.
Yeah, I really appreciate everybody's attendance today.
fantastic example of Analytica and how you're using it, Rob. I really appreciate your time and kind of reworking this presentation a little with us. So thank you.
Absolutely. Yeah.
Yeah.
Enjoy the holidays, everyone.
Yeah. Happy holidays.
Okay. Thank you.
All right.
Bye-bye.
Bye.
Bye.